One of the most powerful tools in working with Laplace transforms is the ability to work with discontinuous functions. And discontinuous functions are functions that are not continuous. The particular one that we'll study in this case is called the Heaviside, named after Heaviside, and it takes on one of two values. It's kind of like a light switch in that a light switch could either be off or on. So 0 we could think about as off, and 1 we could think about as on. And so we have this notation that we use, u with a subscript of a. Now it's a function of time because it's going to be equal to one value if time is less than a, and it's going to be equal to another value if t is greater than or equal to a. So notice that the a here and the a here are exactly the same. So if, for instance, we took a look at the Heaviside function, u sub 2 of t, well, what that would look like is it would take a signal of 0 for t is less than 2, because that's the subscript we chose to use here, 1 if t is greater than or equal to 2. All right, so there we go. There are our values. And so let's think about what this looks like graphically. So for a period of time, and then we'll just plot u sub 2 of t on the vertical axis, we know that up until a certain time 2, I'll just put a tick mark here for time 2, the signal will carry a value of 0. So up until time 2, we'll have a value of 0, an output of 0. And I'm going to put an open circle at time 2 because, well, at time 2, the signal switches from a 0 to a 1. So we switch from a 0 to a 1. I'll put a 1 here. And now from time 2, beginning at time 2 and onwards, a signal of an output of 1. And that's essentially it. It's either a 0 or a 1 values that this guy can take on. And you can see that it's piecewise, or what we call discontinuous, because at time t equals a, and t equals 2 in this case, we have a discontinuity. Okay, before we delve any deeper into this, we will want to think about functions and their shifts. Okay, you'll see this in a moment. So recall that if you have a function, f of t, and you replace the input t with t minus a, that shifts the function's a units to the right. If a itself is negative, then you get t minus a negative, which would be t plus something, and that would shift the graph to the left in the opposite direction. So here, take a look at these two functions. We have f of t equals t squared, g of t equals t minus 2 quantity squared. So notice that g of t is simply the function f with t minus 2 inserted for t, right? So here, notice that t appears here and t appears here. In f of t minus 2, notice that our input is t minus 2, and so all we're doing is replacing the input with t minus 2. Graphically, what this will look like is if you plot y versus t for t squared, you get a parabola. Right? I'll just draw the 1/2 of it. This would be the plot of t squared. Now, as far as what does this graph look like if we plotted t minus 2 squared, well, it will shift the entire graph 2 units to the right. And if you think about why, it's because here, when t is 0, y is 0. We get that ordered pair right there. But when you take 2, it requires that the t value be higher to produce that same output. Okay, higher value of t means that we're moving to the right. So a value of t equals 2 will give us 2 minus 2, which is 0, and 0 squared is 0. So that shifts this point 2 units to the right. So notice that we basically moved every single point. We moved every single point 2 units to the right. Now, if it were t plus 2 squared, it would move in the opposite direction, because if you think about what t plus 2 squared is, well, that's going to require a much smaller input to generate the same output. So for an output of 0, you would need a t value of -2, and so that would actually make the graph shift. It's kind of weird to think about, right? Because usually we want to think about positive as to the right and negative as to the left. Okay, well, in and of itself, the Heaviside function is not all that interesting. It's either a 0 or a 1. But if we get creative, we can actually engineer certain behaviors by using the Heaviside function. So suppose we want a signal of 0 until time equals 2. Okay, so graphically what we're going to be looking for is up until time 2, we want an output, and maybe just call this y versus t. Up until time 2, we want a signal of 0. Let me plot a 1 on here as well before I change colors. All right, so we want it to look like this. Nothing out of the ordinary. But at time 2, we want a signal of 1. Okay, so that seems like a pretty standard Heaviside. But then at time t equals 4, the signal goes back to 0. So here we get our tick marks, we'll say 3 and 4. So we want that signal to be equal to 1 up until we hit time 4. And then at time 4, we want the signal to drop back down to 0. So it's as if we just turned on the switch for just a little bit, and then we turned the switch back off, and that's all that happened. Well, this is some combination of Heavisides. It can go perfectly from 0 to 1. Now, if we just did u sub 2 of t, and I think what I'll go ahead and do is I'll create a little t-chart here to look at the value of time and the output of that function. Now, I am also naturally going to create a column for u4 of t. The reason I'm going to do that is because at time 4, something happens as well. So let me just take a look at the Heaviside with respect to that time. And I'm just going to pick integer times here. 0, 1, 2, 3, 4, and then 5. So let's think about what happens to each of these two Heavisides. So our thinking is it must require some Heaviside at time 2 and then perhaps some Heaviside at time 4, because again we get a signal change. Yes, it goes from 1 to 0, but let's take a look at these signals. So up until time 2, u sub 2 is going to be equal to 0. Then at time 2 and onwards, the plain Heaviside, u sub 2, will always carry on a 1, going back to our original definition, right? u sub 2 will be 1 for all time after that. But u sub 4 will be 0 until time 4. Up until time 4, it'll be 0. And then at time 4, u sub 4 jumps to a 1. And then it remains a 1 for all time, right? These are just going to be 1, 1, and always 1s after that. So what I'm going to do here is I'm going to engineer a combination of these so that what I get is the desirable outcome. So here's what I desire. I'm just going to say desired. What we want to see is at time 0, we want a 0. At time 1, we still want a 0. That's right here. And then at time 2, we want our output to jump to a 1. At time 3, the signal is still at a 1. But at time 4, the signal drops to a 0 and then remains 0 for all time after that. Now, the reason I say this is because let's look at how we could combine the values that we have. So in this case, we see that both of these are a 0. We get an output of 0. So one thought process is, well, maybe it's the sum of the two values. Plus 0 equals 0. 0 plus 0 equals 0. 1 plus 0 equals 1. 1 plus 0 equals 1. But then fails, right? Because then we get 1 plus 1 is 0. 1 plus, which is not 0, which is 2. Well, what if we took the difference between the values? 0 minus 0 is 0. 0 minus 0 is 0. 1 minus 0 is 1. 1 minus 0 is 1. And then look, the u sub 4, if we still do that same pattern, 1 minus 1 is 0. 1 minus 1 is 0. So if we take the output of 2 and we subtract away the output of u sub 4, then we'll get precisely the output values that we want. So our answer is that we should use the Heaviside that activates at time 2 minus the Heaviside that activates at time 4 will give us precisely this graph over here. And we'll just say equals. So it will be 0 for time less than 2. It'll be 1 for beginning at time 2, but not including time 4. And then it will return that back down to a 0 for all time greater than or equal to 4. And so there we have our perfect engineering of a Heaviside function to get it to do exactly what we want.